Let's do a quick review of recurrences. So what are recurrences? Recurrences are basically a tool that we're going to use to analyze the complexity of recursive functions. And a recurrence, or a recurrence equation, is basically a recursive equation. It's a mathematical function that refers to itself in its definition. So the basic structure that we've created in a previous module is that we'll represent the idea of a recurrence as estimating the amount of time that something's going to take for now. And we'll use a generic function for that. So t of n, where t kind of basically indicates time. We also need something that represents the work that's not being done recursively. So any sort of code we look at will have a recursive part and a non-recursive part. We'll generically refer to the recursive, non-recursive part as taking amount of time that's based on another function, f of n. So again, it depends on the problem size, or it may, to be generic. We also want to represent how much smaller a problem gets for the recursive part. So we will again use a function, g of n. So again, the recursive part will work on a sub-problem, a smaller part of the problem. We'll use g of n to describe how the size of the problem changes for the recursive steps. Okay, so we looked at equations of this form. The amount of time taken for a problem of size n is a combination of the amount of time it takes in the non-recursive part of the function plus recursively processing a smaller problem, where the smaller problem is defined by g of n. So our overall goal with recurrence equations is to come up with a simple closed form expression for them. So we don't actually have the recursive part anymore. Basically, we want a simple equation that has a fixed number of operations. So we looked at two approaches for this last week. One of the approaches was the substitution method, otherwise thought of as guess and prove. The basic idea here is that you can, if you can make up or find a good guess, which I'll refer to as h of n, then you can try a proof by induction, and using a base case and induction, you can try and demonstrate that beyond some sort of an initial start point, your proof is correct. So again, proof by induction, you'll have a base case, you'll have your start point, you'll create your inductive hypothesis and try and demonstrate that for every place past your base case that your inductive hypothesis induces the fact that it continues to be true. Okay, so the real downside of this is that it only works if you have a good guess. If you don't have a guess, if you can't inspect your code or your recurrence equation, come up with a reasonable guess, then you can't really make any progress with this approach. If you have a good guess, it's useful because you can't actually prove that your guess is correct. Okay, so we want a simple closed form expression, and we also looked at another approach to derive the closed form expression. So we looked at using a recursion tree and doing some accounting. So that works for certain types of occurrences. Okay, so this gave us tools to study the general form of recursion, and we applied counting to identify the total amount of work that was being done. So let's do a quick review of two examples that we looked at previously. So we had this recurrence, t of n equals t of n over 2 plus c. So the n over 2 kind of indicates that the problem size is being cut at each recursive call, and the c indicates that we're doing a constant amount of work on each recursive call. Okay, so we drew out diagrams that would look something like this. We would basically create a node that would represent the amount of work being done at each call. So for our first call, our problem size is n, and we'll do c units of work. And then the function will recursively call itself with half the size. So we'll have another c units of work when our problem size is n over 2. And then the process will repeat itself. We'll have another c units of work when our problem size is n over 4, and so on and so forth. So this leads to the question, how many total steps or links are there going to be in this chain? And we simplified the problem last week a little bit, and we assumed that n is a power of 2. Based on that, The total number of links in this chain, as we saw in previous classes, was log base 2 of n. So our total amount of work we can then derive. So our total amount of work goes from a depth of 0 to a depth of log base 2 of n, and we're doing c units of work at each step. So we can represent that as a summation, and we can apply our rules of summation in basic algebra, and we can simplify it to big theta notation. So basically we're doing log n units of work. We've got some constant times log base 2 of n plus 1. So simplifying and dropping the constants and coefficients, theta of log 2 of n. Okay, we also looked at another example of this accounting approach with a more complicated equation. So we had t of n equals 2 times t of n over 2 plus c times n. So in this case, our amount of work being done at each individual node is a little bit more complicated. It's no longer constant. It depends on the amount of the problem size at that instance. And also, our recurrence is a little bit more complicated. It looks like we're splitting our problem into halves, and then we'll be doing 2 recursive calls on those halves. Also, as is often the case, we had some sort of a base case or special condition. In this case, we had a different amount of work being done at the leaf nodes when there weren't recursive calls than there were on the recursive calls. Okay, so what's a little bit different about this is each node is doing a little bit different amount of work. It's doing c times n. And there are the 2 recursive calls. So each time the problem size gets cut in half, but we're doing 2 different calls. So each one of them is doing its c times n units of work. Of course, n is half of the original problem size here, so it's c times n over 2, and so on and so forth. Okay, so we've seen these 2 different approaches. We've seen how if we know an appropriate closed form of our recurrence, we can prove that it's correct, and we've seen how we can use accounting techniques to try and come up with a representation of the closed form equation. Now we'll move on to our third approach, the master theorem and its application in the master method.